Yes, no notes.
Yeah, a couple of notes.
All right. So let's go through this PowerPoint here. This is a continuation of the PowerPoint we started. I think it was what, Monday or Tuesday this week. We did a PowerPoint on this, and then after we're done with this, then we're going to talk about the little assessment that I did yesterday with you guys in class. Where you have your Chromebook, and I wanted to see kind of where you guys were sitting with some of this stuff. So let me hit the lights here, and then we'll go through some stuff. So the whole section we're in is the Pythagorean Theorem. This is one of the last days we'll cover it. It's one of those main staple theorems we need to know. The big thing today, I want to talk about Theorem 8.4 again, give you a couple examples of it, give you kind of a real life problem that we can work with this. And then we're going to go through a couple new theorems today, which are the Pythagorean Theorem again. I know it's weird. They have three theorems that are the Pythagorean Theorem over and over and over. Okay? Because they want to talk about, they want to talk about how do you use it? Like, if it's not a right triangle, what could you use the Pythagorean Theorem for? And that's what we're going to talk about today. That was that last problem on that assessment I gave you yesterday, was hinting at the fact what we're going into. And I want to see if somebody can connect the dots there. Question?
Is this a theorem like where you connect it to nature, like the time zones?
No, that's the Fibonacci sequence.
Oh,
yeah.
We need to learn about that.
When do you learn about that?
When we get to.
Oh, sequencing? We already did some form of sequencing back in chapter 2. It was the beginning of chapter 2. I don't know if it comes back up if we actually go through series, like Taylor series and stuff. I'll look to see if that's on the docket. That might be like an end of the year topic if it's the last section. I'll have to look at where it lands. So, alright, but anyways, these are our topics today. We are going to get new homework today, which I think it's like 13 problems, something like that. It's pretty easy. It's just Pythagorean Theorem. So if you know how this works, it'll be pretty straightforward. It's nothing, you're not doing proofs or anything like that. It's calculations. You need a calculator for it. Obviously, that's what we've been using the last couple of days in here. So hopefully that makes sense to you. So, all right. But let's go through some of these. So again, this homework will be due on Monday the 12th. So you have a couple days to work on it. I'll give you some time today, some time tomorrow, like kind of what we've been doing all week. But tomorrow we're going to start more or less kind of working on the last section of chapter 8. I've tentatively set the review to start possibly as early as Monday next week, Monday and Tuesday. That way we can take our quiz over chapter 4, chapter 8 mixed together as early as like Thursday or Friday next week. I haven't set like how many problems are on there yet. It might be just like a one-day quiz kind of a thing, like a pop quiz, where we just, we do a couple problems on Pythagorean Theorem, a couple of properties on triangles itself, like isosceles and stuff. I don't know how many problems I'm necessarily going to put on there, so it's still kind of in the works. So, but you're going to get a practice guide. I promise you that, and then we can kind of figure that out. All right, Pythagorean Theorem. This one we've been working on the last couple days. You've already written this down multiple times. This one I showed you yesterday in class. It has to work for a right triangle. So that's the Pythagorean Theorem. It works in a right triangle. The sum of the square of the legs. So these are the legs. A and B are the legs. How I know that? They're touched at a 90-degree angle. So you square the legs, and that equals the square of the length of the hypotenuse. That's letter C. The hypotenuse is always the big wall, the wall that doesn't touch the right angle. So in other words, this is the formula you should have written down. Now, we did an example yesterday. Whoa. That's not what I wanted. I don't need that to be. Just work. Just work. That's odd. Just work.
I guess it's just telling us to watch TV.
Okay, I don't know what's going on. It just suddenly works all of a sudden and it makes noises. Okay. Ooh. Alright, so let's do an example of this where I put like kind of a real story problem behind it. I think one of the problems that I did with one of the classes was we had a water tower. So here's my water tower. It's a terrible water tower. It looks like a big balloon. Alright, let's compare a water tower. There we go. Alright, and let's say we wanted to find how tall it is. Okay, this is the number I want to find. That's my question. How tall is the water tower? But for some reason, you know that there's maybe a cable going from the top to the bottom. Maybe there's some length of cable there. Let's say that's a 100-foot cable. Okay. And you are standing, from that base, where the water tower is right here. Maybe that's the direct base of it. There's like a little plate here. from the base over to that spot, let's say that that's, I don't know, 60 feet, something like that. We can figure out how tall the water tower is. That's using Pythagorean Theorem. It's just a right triangle, simple. We don't need to turn the picture. I just want to make it look like an L. So if you need to have it, set up like this, it's fine. The two legs are these two parts because they touch the 90-degree angle. The hypotenuse is that one. So when you plug those numbers and the variable, I guess, into your formula here, you just have to make sure, and this is the part that I would, write down. You need to put the legs over here, whatever they are. I don't care if like one of the legs is missing, or maybe you have both legs. You have to put the legs for A and B, and then the hypotenuse is this one. The hypotenuse should always be the long side, it's always the one by itself. Whatever they give you, you have to square them first. So, in my case, I don't have letter A, I'll call it x, so x squared. You're going to add that to the other leg, which is 60 squared, and set that equal to the hypotenuse squared, which is 100 squared. That's how you set up your formula. It's always the two legs squared, that means power of 2, not a square root, but a square. You add those together and that equals the hypotenuse. So the idea is that 60 squared is 3,600. 100 squared is, I believe, 10,000. You would subtract that over. So to subtract this across. So that turns out to be 6,400, I believe, if I'm not mistaken. Let me double check my math. I think it's 6,400. And then, because again, I would subtract that number across because I want to get the x by itself, and since there was a number being added to it, that's why I subtracted 3,600 across. And there's a power of 2 on it. And how do I get rid of the power of 2? Square root, right? So you take the square root of the 6,400, and that gives me, my answer is 80, and that would be in feet. So the water tower would be 80 feet tall. It turned out to be a nice, pretty number. It's one of those Pythagorean triples. All right, questions with the idea of how to use the Pythagorean theorem? Like, that's a perfect example of like a real life problem you could actually do with that. Okay? Or maybe you have the height of the object and you know how far you're standing away from it. Maybe you need to know how big the ladder is leaning up against it. That could be something. Maybe you want to know how big of a ladder you need. So let's do an example like that. Let's do one of those here in a second. But this is a good example of like a real life application based problem. You can find heights of objects by just knowing simple things about a triangle. Okay, I think that the formula is actually really simple, but again, you would have to actually like type these in a calculator, especially if you didn't know how to square a number or take a square root of a number. And again, this could have turned out to be a decimal. I just made up these numbers. So they could have been decimals. I know a lot of us that we were doing problems yesterday, I had to just make up problems. A lot of people were getting decimals. That's fine. You can have that. Go to 1 or 2 decimal places. In fact, the next problem we're going to do, I'll let you make it up. So you can make up some numbers here. Okay. And try not to use 80, 160. Let's try to use different numbers. Okay, let's do another one, and then we'll get to the new stuff today. All right, so let's do one more. Hopefully we'll get some numbers. This time we're going to find the height, or we're going to find the length of a ladder. So we're going to put a ladder up against something. Let's say we're going to put a ladder up against let's do a tree here. So here's my tree. It looks like broccoli. Just go with it. All right, there's my broccoli tree. All right, there's my tree. Okay, and we're going to put a ladder up against the top. Maybe we have to get a cat out of the tree. Okay, we got a cat. Really getting into this story here, I guess. All right, here's my cat. All right, there's my cat. It looks like a monkey. Just go with it. All right, anyways. We're putting a ladder. I don't know how big a ladder I'll need, but how big is our tree? Say it?
70 foot.
70 foot. Okay, we got a really tall tree. All right, so that cat monkey thing is 70 feet up in the air. That looks terrible. All right, I'm nervous. How far are we standing from the tree?
12 feet.
Okay, I heard 40. That was the first number. Sorry, I heard 40 feet. I like the 12, but we're going to stand 40 feet from the tree, and this is where we're standing. We need to go rescue our cat. All right.
Monkey cat.
Monkey cat. All right. And the idea is I want to figure out how big of a ladder I need. Is it even possible to have a ladder that big? That's really the question, because maybe it's like way big. Because I already know, like when we're trying to find a ladder, what does it have to be bigger than right now?
Tree.
It has to be bigger than the tree, right? The ladder has to be the biggest wall. So it has to be bigger than 70-foot ladder. So this is a big ladder. Okay, it's not a 50-foot ladder. We might be pushing 100 feet or more. So we're gonna have to figure that out. Okay, now again, the legs are these two. Those are the two legs of my right triangle. The reason being is that they touch the 90-degree marker. So we have the height, we have that other number, we have to find the ladder. So 70 squared plus the 40 squared, because those are my two legs, and I'm gonna try to find the hypotenuse. That's the ladder, that's the one number I'm missing. Again, on this one, we're just missing the hypotenuse, so that's the wall that's by itself. 70 squared is 4,900. 40 squared is 1,600. To add those together, that's a 0, 0, 5, carry a 1, that's 6,500. And then you take the square root of it, which is a weird crazy decimal. That's 6,500. It's just above 80. It's somewhere like 80.
80.62.
80.62 feet. 80-foot ladder, if that's even possible to buy something like that. Maybe it is. I don't know. I don't think so. Okay, you could try it. You might have to call the fire department or try to attempt to climb that weird tree.
You're 70 a tree.
Yeah, or probably a tree. Or just leave the cat there. Okay, so.
Cat life standard.
Get up there. He's got 9 lives. It'll be fine. Alright. Yeah, how do you get up there? That's a good question. He's a monkey. He can climb. Alright, but anyways. That's the types of problems we're gonna have today. Now, obviously, you're not gonna have weird drawings. They'll just give you the picture of the triangle. They want you to find one of the parts. I think it's pretty straightforward. As long as you're typing in your calculator and you know how to get that. Remember, when you type in squares, the trick is just take 70 times 70. Just write the number down. Take 40 times 40. That's what a little power 2 means. And when you do the square root, for a lot of people in here that have these calculators, these calculators, you can just type it, you can just hit the square key. The square key, you have to hit like the little second key, then the square button's right here. You can see it's in yellow, and then you can type the number behind it, like 6,500, and then hit enter. Right? If you have a non-menu driven calculator, like, I got a number here, I think somebody borrowed this the other day. My little Dollar General thing that I bought years ago. You can type in the 6,500 first, and then hit the little square button. And it gives you the 80.6. Add it. Alright. Questions? Moving on. Here we go. Alright. Enough of weird stories. Let's get to the actual properties today. Okay, new one today. Now, as I said, our 3 new theorems are all the Pythagorean theorem over and over and over. So you don't have a new formula. It's all the same formula, so don't stress that you have new ones. It's just the same formula, but here it is. Okay, so these are called the converses, right? And we can figure out how to use these. So the converse of the Pythagorean theorem says the sum of the squares of the lengths of the shortest sides, which are the legs of a triangle, is equal to the square of the longest side. Then the triangle has to be a right triangle. So it's going backwards. We don't know it's a right triangle, but somehow the math works for the Pythagorean theorem, then it has to be a right triangle. That's what this theorem is saying. That the only way you could have a right triangle is if the Pythagorean theorem works. So notice, this picture does not have a right angle. It does not. But if I were to do the Pythagorean theorem to it, so a squared plus b squared, if it's somehow equals c squared, whatever these numbers are, if that actually does work, that they are equal to each other, well, this theorem says it has to be a right triangle. So you can put the right angle in between the two smaller walls. So why this is useful? Now we can use the Pythagorean theorem to actually check what kind of a triangle you have. It's the one thing that a lot of kids don't know you can do. You can actually use it to actually tell, is it a right triangle in the first place? Or is it a different type of triangle? Okay, but again, we're just using the Pythagorean theorem. If it does work, then it has to be a right triangle. Okay, so we're going to make up some numbers. I want single-digit numbers only. Now, I know you guys are still writing, it's fine. You're just writing the Pythagorean theorem over again. But I need 3 numbers, 2 small ones and a bigger one, and we'll talk about it. 6, 8, and 6,
10.
8, 10. Okay.
Isn't that the...
This is Pythagorean
Yeah.
triple. Yeah. It's the numbers we used earlier. All right, we'll go with it. I like it. All right, so we have 6, 8, and 10. Now, why did I put them in those locations? The 10 had to be the bigger wall. And one of the other things you have to know about triangles is that when you add any two walls of a triangle, this is just a common sense thing you should know. When you add any two walls of a triangle, they always have to be more than the third wall. It works in any type of triangle. Any two walls you pick the 10 and 8. When you add them, it has to be more than the third wall, the 6. When you add 6 and 8, that has to be more than the other wall, the 10. Because when you go a triangular path, that is longer than the shortcut cutting straight across. So what I mean by that, when you add 6 and 8, that's going around the block, that should be a longer distance than somebody just going straight home. So it didn't matter which two walls you pick, it should always work that way. If you have a triangle that doesn't, let's say you have something like this, and you did 5, 7, and you said that this was 13, that's not a triangle. Because two walls don't add to be more than the third wall. It's not actually a triangle, it's actually drawn incorrectly. It's supposed to be like this. Okay, that wall is actually too long compared to the other two. Because going around the block should not be a shorter distance than somebody walking straight home. Just saying, it's common sense. But anyways, what this theorem is saying is that when you do your squares, you take the two smaller walls and you square them. If it somehow equals the bigger wall squared, it is a right triangle. In fact, you guys just happen to pick perfect numbers. This does actually work to make 100. And that is 100. Crazy, you guys actually picked numbers that worked, and yeah, it's the right triangle. So good choice, good pick of numbers. Okay, questions about that example, like how you can use it. Okay, now, you're probably thinking, okay, well, yeah, if they work, it's a right triangle. What if it doesn't work? That's the other theorems. So, no matter what numbers I give you, we can check what type of triangle it is. Okay, is everyone good? Does everyone have it? Alright, next one. Again, these are all the Pythagorean theorems, so if you're writing these, you're just rewriting the Pythagorean theorem over and over and over. Alright, so you square the lengths of the legs, or I should say you square the length of the longest side, and somehow that turns out to be less than, it turns out to be smaller than the sum of the other two sides when you square those. Then what you have is you have an acute triangle. So in other words, you do this type of thing, where the hypotenuse, when you squared it, turned out to be smaller than the other two added together. So I'll give you your triangle here. Now again, I'm just using the same picture over and over and over, but I'll give you an example here in a second. Okay. So again, the hypotenuse somehow when you square it, turns out to be less than the other two. Okay? So for instance, let's say I was doing 8 here. This is 8. This is 9, and this is 10. I'm going to use those numbers. Okay, so 8, 9, and 10. You square each wall, and the two smaller walls are the legs, right? If this turns out to be a right triangle. So you square the two smaller walls, and you add those together, and somehow that turned out to be bigger than the 10 squared. Which it is, right? This is 64, this is 81. That is most definitely bigger than 100 when you add them together, right? In fact, that's a 5, it's what, a 145? So it is most definitely larger than the hypotenuse wall. They're not equal, one side's bigger. The hypotenuse turned out to be too small compared to the others, right? This is too small. So if the hypotenuse is too small, then you have an acute triangle. That means all the angles inside the triangle are less than 90. So in fact, my drawing is actually really bad. It should be more something like this. Or 10, 9, and 8. That's what it should look like. It should be an acute triangle, not a right triangle. Almost looks isosceles, but it's not. Just a number off.
So yesterday on the last question, we were looking numbers supposed to be acute.
Mm-hmm. Yeah, so we're going to actually go ahead and look at that. I'm going to pull that drawing up. But again, how you know this is if the hypotenuse turns out to be too small, then it's a small triangle. The hypotenuse tells you everything. If the hypotenuse is equal, it's a right triangle. If it's too small, it's acute. So that big wall will tell you everything. Okay, but again, it's just using the Pythagorean theorem. It's just you're trying to figure out, is it equal or not? Now, I think you can probably figure out what the next one says. The next theorem. So instead of saying the hypotenuse is too small, now it'll say it's too big. And we'll look at an example of that. I'll make up some numbers here. We'll go to that here in a second. Okay, we good so far? Okay, has everyone got it? That's some people are still writing. Mac, you good? You're starting?
Yeah.
Alright. Mitch, you good? Nelson, you good? Okay, alright, I'm gonna move on to the next one. Okay, so let's do another one here. Again, we'll just try to pick out numbers that makes this thing work out nice and pretty. Alright, so again, this is the last theorem of the day. Pythagorean Theorem, you square the longest side, and somehow that turns out, when you square the longest side, it turns out to be greater than the other two legs squared. But it's still a triangle, right? Those triangles I've been giving you are all triangles because you can add two walls and it's always bigger than the third wall. But this says when you square them, if the biggest side turns out to be bigger than the other two, then it's an obtuse triangle. So in other words, you do the Pythagorean Theorem, and that hypotenuse is bigger than the other two when you square it. So I'm going to give you a picture again, and let's throw some numbers in here. So let's say we do something like, let's go 7. Let's go 7, 6, and 2. Yeah, let's do that. Okay. Now, just to test if this is a triangle or not, I always do that. When you add any two walls, do they make bigger than the third wall? Okay, so it is a triangle. Two walls always have to add to be bigger than the third wall. That's common sense when you look at a triangle. Because when you walk around the block, there should always be more. That should be always a bigger number than the path straight home. So these numbers do work. But when I square the two smaller walls, and I square the larger wall, you can see that the larger wall turns out to be too big, right? This turns out to be 36, and you're going to add 4 to it, and this turns out to be a 49, and you can definitely tell the 49 is too big. This turns out to be 40. So the hypotenuse is way too big. This is too big, right, compared to the other two added together. So it had to be obtuse. There's an obtuse angle. Not a right triangle, but it's obtuse. Now, like if you didn't hear Nelson earlier, she was asking about that last question we did in that little assessment. I wanted to see where you guys were yesterday. So I'm going to put that problem up on the board so you can see it. Now again, I would never even do this test. It's really a test. I would never do this test if it's not a triangle. Like if my little rule of thumb where I add two walls together, if I had two walls and it's not bigger than the third wall, I would never even attempt to do this thing because it's not a triangle in the first place. So I wouldn't even test if it has obtuse right or acute angles. All right. Questions, comments at all about any of these? Is everyone good? Everyone's got it? I'm going to put the examples I did on the board yesterday. The little assessment thing we did from the Google Drive. And I want to see what you guys have here. Everyone's good though? Okay. Here are these numbers. Let's just take a look at that last problem. All right, we've done enough Pythagorean Theorem. I think everyone kind of knows that. But I want to show you that last problem we looked at yesterday. All right. This was the thing that I handed out yesterday. I think you were the only one that didn't get this thing yesterday, correct?
I didn't finish it, of course.
Yeah, so I wasn't worried about it. I was just kind of testing where people were at. All right, so here's the idea. Okay, the first problem you had to find a missing wall. That's really a lot like your homework problem. So if I was doing the Pythagorean Theorem, these are your legs. So you square these two, add them together, and say equal to the 50 squared, and then you just solve for x. You have to take a square root. It should be a number, right? The same, these are the legs here, the 40 and the 48 and the 20. So you square these, add these together, set equal to x squared. So that's your hypotenuse. Those are a lot like your homework, then you wrote down your answer. We talked about, that video of the Wizard of Oz, talking about the Wizard of Oz had the quote wrong. He was trying to be all smart, he got his brain. But he talked about the square roots of any two sides of an isosceles triangle. well, first we're talking about right triangles. He was talking about square roots. We square things. And they couldn't be any two walls. They had to be the two smaller walls. And then he kept going and he kept getting it more wrong. But it was just kind of a funny little quote. But this is the last problem that I had. And we didn't really talk about it because I want to see if anyone can connect the dots. And some people actually did. They actually kind of figured out during the day like how you could do that problem. But if you're drawing a random triangle, okay? I don't know if it's a right, acute, or obtuse. If you're drawing a triangle, where did the 7, 14, and the 16 need to go if it was on a base triangle?
16 is the hypotenuse.
Yeah, it had to be the hypotenuse in theory, right? Because it was the biggest wall. Then the other two could be, the 7 and the 14. Those could be the other two because those are smaller. Now, is it a triangle to begin with? Mm-hmm. Yeah, because when you add any two walls, it doesn't matter which two you pick, it's always more than the third wall. So it is a triangle, so yes, this is a triangle. Now I just have to figure out what type, and that's the new stuff we learned today, right? So you take the two smaller walls, you square them, and we gotta figure out how that's related to the third wall squared. So 7 squared is 49, 14 squared is a 196, 16 squared, oh man, what is that? Is that a 256?
Yeah.
Yeah.
Okay, and you add these together, and what do you get? You get a 5, carry a 1, that's 14, carry a 1, that's 245 versus 256. Let me double check my math, I can't add in my head. I can do everything else, but I can't add. But that's what we get. So it looks like the hypotenuse turned out to be too big, correct? It was like bigger than the other two. So what type of triangle is that? It's obtuse. The hypotenuse tells you everything. If the hypotenuse is too big compared to the other, when you square them, then it's obtuse. If the hypotenuse is too small, then it's acute. If it was equal, it's a right triangle. That's what you're hopefully getting. But it was obtuse. All right, questions at all about that problem we did yesterday? I just thought it was kind of an interesting problem. It was something that I want to see if anyone could figure out, connect the dots there. I wasn't expecting people to get it right. I just want to see kind of where you work. All right, homework today. Okay, and remaining 10 minutes left of class here, but homework today, go back. Oh, there. This is due Monday, page 551. So here's your problems. They are all triangles. They just give you a picture. They say, find the wall that's missing. It's Pythagorean Theorem over and over and over. There's only a select few in there. There's a select few in here. There's a select few over here. I think of these last 3-ish. They ask you, is it a triangle or not? So you have to do that little check. Is it a triangle? What type is it if it is? If it's not a triangle, just say not a triangle, move to the next one. If it is, then you have to do the check. Is it obtuse, right, or acute? That's it. It's pretty simple. I'm honest when I tell you that I would not expect this homework to take you more than 10 minutes. I'm not even joking. Like, it's just Pythagorean Theorem, you solve for a wall, you move to the next problem. Okay, you're using your calculator 99% of the time. So I think it's pretty straightforward. Now again, the only time that this could be confusing and maybe you don't know how to use your calculator correctly, like you find a square root. If you get square roots, it's fine. Give me the decimal, 2 decimal places, you're fine. I just want to know roughly what those wall lengths are. Try to show some work, but I'm not joking. It should not take you more than 10 minutes. All right. Rest time is yours today.